Hello there, it's Dr. P. In this video, we're going to talk about binary multiplication. Multiplication is another critical arithmetic function. Imagine doing a math assignment without multiplying even once. We multiply all the time, so computers need to be able to do this too. Multiplication is the trickiest of the three arithmetic functions we'll do in this class, and it's also the hardest to carry out in a computer CPU as well. As you'll learn in this video, multiplication makes use of shifting, multiplying, and adding. It's an iterative process that takes some time to carry out. To build hardware using digital logic that can multiply takes some serious effort. Either a hardware multiplier is fast but takes up a ton of space and is extremely inflexible, or it's slow but can be used in a more efficient manner. Microcontrollers, such as the one used in the Arduino, can actually brag about their really great proprietary multiplying hardware because it's just that hard to carry out on chip. Hopefully I haven't scared you off. Multiplication isn't hard, it just takes time. And there are some tricks we can use to help make the multiplication process as easy as possible. As with all of the other signed arithmetic we've done so far, we need to know the number of bits that our system is constrained to. We also need to be aware of overflow. How do we check overflow in signed binary multiplication? It's not as simple as it was in addition or subtraction. What we need to do is generate overflow bits. So what we do is we start with our 2's complement binary number, and then we double the number of bits by adding an equal number of bits to the left. The value of those bits will be identical to whatever the sign bit is. So if I have a 4-bit system and my number is positive, I'm going to add 4 zeros to the left of my number. If I have a 4-bit system and my number is negative, I'm going to add 4 ones to the left of my number. If there were 5 bits in the start, then I'd add 5 overflow bits to the left, and so on. The burden of overflow bits isn't just a constraint for our pen and paper calculations. It's also something we need to include in hardware. So you can start to get an idea for why multiplication is tricky to do in hardware. I would need to be able to store 2 times the number of bits that I want my system to use. A typical 8-bit system, therefore, would need 16 bits of memory just to do multiplication. Next, we need to really understand the process of multiplication. So let's do an example with base 10 numbers first, just so you can see what I mean. Let's multiply 352 times 56. I know, you thought you would never have to use your times tables again. I promise that binary multiplication is actually much easier than decimal multiplication. And it is, but bear with me. So we start with the ones place in the multiplicand, which is 6. We multiply 6 times 2, and we get 12. Then we multiply 6 times 5, and we get 30. But we got to add in that carry. I promise we will not get multiplication carries when we do this in binary. Then we multiply the 6 times 3, 18, plus the 3 is 21, and then that carry comes down. So we're done with the ones place in the multiplicand. What we do is we put in a spacer, and we move to the tens place in the multiplicand, which is 5. So 5 times 2 is 10. 5 times 5 is 25, plus that carry. 5 times 3 is 15, plus that 2 is 17, and that carry comes down. So I could keep going with the multiplicand, but if you realize we've got invisible zeros to the left, so if I were to switch to the hundreds place, then I would be multiplying by all zeros. So once we get to the end, or where we have all zeros, we are done with the multiplication part. But we're not done with the answer, right? The answer is not 2,112. The answer is not 17,600. What we need to do now is add these. So adding should be simple. 2 plus 0, 1 plus 0, 1 plus 6, 2 plus 7, and 1 plus 0. So the answer is 19,712. My TI-83 calculator tells me that I didn't mess this up, which is very good to know. So the point of this, again, was to get at the process of multiplication. 1. Multiply each bit in the multiplicand, shifting the answer over each time. 2. Add up the products to get the solution. This is the same process we use in binary. But the great thing about binary is that we have a much, much easier times table. This comes from the truth table for multiplication. I love this because I get to multiply only by my two favorite numbers, 0 and 1. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. Isn't that the best times table ever? Okay, now we get an idea of the process. We know what our truth table or our times table is. So how do we know if we get an overflow at the end? At the end, after we have added up all of our products to get a solution to our problem, we're going to have overflow bits, a sign bit, and then magnitude bits. All of the overflow bits must be identical to each other, and they must be identical as well to the sign bit. Let's assume that we just did 5-bit binary multiplication. That means I would have 5 overflow bits, 1 sign bit, and 4 magnitude bits. These are 3 hypothetical solutions that we got to 3 different hypothetical multiplication exercises. In this top solution, the overflow bits are identical to each other, so that's nice, but they're different from the sign bit, so that means this was an overflow. The second solution has all of the overflow bits and the sign bits in complete agreement, so that means that this answer was not an overflow. This one was valid. The bottom solution has disagreement between the overflow bits, so that one's also an overflow. So now we know how to find an overflow given a final product. One more thing before we finally do some examples. This is a multiplication life hack. You want to make sure that the binary number with the most ones is the top number, known as the multiplier. Trust me on this. You want as few ones as possible in the multiplicand, because each one in the multiplicand is another addition step. Oof! Okay, let's try some examples. Our first example will be to multiply 3 and -2 in a 4-bit binary system. So we take those two numbers and convert them to 4-bit 2's complement numbers. 0, 0, 1, 1 is 3, and 1, 1, 1, 0 is -2. We need to then add overflow bits. So 3 is going to get 4 zeros to the left, and -2 is going to get 4 ones to the left. But remember that life hack that we want the number with the most ones to be on top? So yeah, let's rearrange those. Now we're ready to do our multiplication. Personally, I'm a very big fan of using grid paper when I multiply. Remember how in 2's complement addition, dragons come in and eat all of the carries that come up to the left of our number of bits? The same thing happens in multiplication, which means that I like to make sure that I've written down exactly how many bits I have so I know where the end of the earth is. What I like to do when I'm doing binary multiplication is I like to take every spot to the left of the numbers that I'm working with and remind myself that that is the edge of the earth, and anything that gets placed in those columns is going to be eaten by dragons. So just as with decimal multiplication and binary multiplication, we start with the ones place in the multiplicand and we multiply. 1 times 0 is 0. 1 times 1 is 1. And then if we notice, we keep getting more and more ones. Our multiplication times table for binary, super, super nice. We put in a spacer, and then we switch to the 2's place in the multiplicand. 1 times 0, 1 times 1, 1 times 1, 1 times 1, 1 times 1. Why didn't I put in that 9th one? Because it would be eaten by a dragon, so I don't need it. Again, I could move to the 4's place in the multiplicand, but it's zeros. All zeros to the left, so that means I can stop. Now I can add 0 plus 0, 1 plus 0, 1 plus 1 is 0 with a carry, 1 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 with a carry. If I look, my overflow bits agree with each other, and they furthermore agree with the sign, so I didn't have an overflow. If I want to double check my answer, I can do that reverse 2's complement process. So I subtract 1, I get 1, 0, 0, 1. I flip the bits, and I get 0, 1, 1, 0. It's positive 6, which means my answer is negative 6, which makes sense because I multiplied 3 and negative 2. Good work! Next, what I'd like to do is multiply 5 and negative 3, also using 4-bit binary. We'd come up with our 2's complement numbers. 5 is 0, 1, 0, 1, and negative 3 is 1, 1, 0, 1. We add our overflow bits. Then we apply our life hack to make our lives much, much simpler. As always, I like to draw off my dragon space. Start with the ones place in the multiplicand. 1 times 1, 1 times 0, 1 times 1, times 1, 1, 1, and 1. Put in a spacer. The 2's place in the multiplicand is a 0. So if I were to do the multiplication here, I would just be getting a whole bunch of zeros. I can skip that. If you really want, you can put in the zeros. You don't have to. So I need to put in a second spacer before I go to the 4's place. 1 times 1, 1 times 0, 1 times 1, and you know why I'm not putting any 1's to the left of that yellow line. We add 1, 0, 0 with a carry, 0 with a carry, 1 with a carry, 1 with a carry, 1 with a carry, 1 with a carry that gets eaten by a dragon. My overflow bits completely agree, but they disagree with the sign bit, which means this is an overflow. Makes sense because negative 15 cannot fit in 4-bit 2's complement. The most negative number that we can have in 4-bit 2's complement is negative 8. Last, let's switch to 5-bit binary and multiply negative 10 and positive 7. Again, I generate my 5-bit 2's complement numbers, and I place some overflow bits to the left. In this case, my numbers are already set up with my life hack in mind. If they weren't, I would really want to make sure that negative 10 is my multiplier and 7 is my multiplicand. All right, start with the 1's place. 1 times 0, 1 times 1, 1 times 1, 1 times 0, 1 times 1, and 1, and 1, and 1. Spacer, 2's place. 0, 1, 1, 0, 1, 1, 1, 1, 1. 4's place. 0, 1, 1, 0, and lots of 1's. Now we have 3 products that we need to sum. Well, remember what I strongly recommended that you do when you have more than 2 numbers that you have to add together? Start by adding these 2, then add the third to that, and get your final solution. Okay, you do not want to deal with keeping track of all of the carries that you would get if you wanted to add all 3 of these at once. It is not worth doing that. All right, so let's take the first 2 numbers and sum them together. And we get 0, 1, 0 with a carry, 0 with a carry, 0 with a carry, 1 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 with a carry that gets eaten by a dragon. To that, we are going to sum this third product. Zero, 1, 0, 1, 1, 1, 0 with a carry, 1 with a carry, 1 with a carry, 1 with a carry. If we look at our overflow bits, off the bat they don't agree, which means that this is an overflow. Makes sense that this is an overflow because negative 10 times 7 is negative 70, and there's no way that's going to fit in a 5-bit 2's complement number. Multiplication is definitely not easy, but again, it's important. So you need to really practice the heck out of it until you feel comfortable with it. Remember, you always need to use those overflow bits, even if you don't feel like it or don't like using them. The overflow bits are a crucial part of the multiplication process. And then you need to know how to interpret your result at the end. So practice, 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 and then practice some more. Until next time, stay well.